Hey, what's up guys, my name is Cherno. Welcome back to my ray tracing series. So last time was a very exciting episode because we actually drew something. We rendered this sphere using the power of ray tracing. If you haven't seen that video yet, I highly recommend you watch it first. The link will be up there as well as in the description below. There were quite a few kind of unanswered questions in that video. There was a lot more that I wanted to show. However, we didn't get the chance to explore everything that I kind of wanted to. So what we're gonna do today is we're gonna dive even deeper into what we did last time, because you guys were very excited about the depth of this series. And we're going to explore a little bit more about what it actually means to like cast a ray. Like how does that work? It's quite a difficult task to actually draw this as a diagram, and that's one of the reasons why I didn't really want to explain it last time. Today though, what I have in front of me is Hazel. We're going to actually write some code here using Hazel, the big version of Hazel, which you guys can access on patreon.com/thecherno. We're going to use Hazel to visualize these rays in 3D space and be able to kind of interact with them and fly around them, which I think will be just a much better way of explaining this than obviously drawing it on paper. Now you could also use something like Unity to visualize all of this stuff, but we're going to use Hazel because it's actually going to be a lot easier and faster to work in Hazel, as you'll see. Now before we get started, I want to mention that this video and this whole series actually is sponsored by Brilliant, which is an absolutely fantastic place to learn all about the math that you'll need to follow along with this series. It's so good that I've actually personally been using it to revise some of the calculus that we'll need for later on in this series. So I'm very serious when I say that it is my favorite place on the internet to learn math. The biggest thing I think that sets Brilliant apart from the rest of the competition is the fact that all of their courses are extremely engaging and interactive. They don't just try and present you with information, they get you to engage and interact with it. And they also present things very visually. I mean, we're literally going to spend today talking about rays and presenting them visually because I think it's just such a good place to learn, and Brilliant is full of that kind of stuff. Aside from math, they've also got plenty of courses on various STEM topics, such as computer science, data structures, actual practical applied science, you know, that kind of stuff. And you can get started with Brilliant for free. Just go to my link in the description below. That's brilliant.org/thecherno. Brilliant have also been nice enough to offer the first 200 of my subscribers 20% off an annual membership if you sign up using my link in the description below. Huge thank you as always to Brilliant for sponsoring this video. So without further ado, let's check out our setup for today. Okay, so what I've got over here is Hazel. I've just made a new project in Hazel. Again, if you want to follow along with this, you don't have to use Hazel, even though I recommend that you do. You can use something like Unity, and the process should be fairly similar. You should be able to replicate this pretty much exactly. Inside our scene, we just have a basic skylight, a camera, and an entity, and the entity is hooked up to this kind of ray tracing series.main script class, which is what you see over here. The plan here really is we're going to implement some of the code that we actually wrote last time. So this is in the last episode. We had this kind of pink sphere being rendered. It looks like it's kind of in 2D space, but as we'll see today, it is in fact in 3D space. We'll see a bunch of extra information about this, which is really cool. We're basically going to kind of recreate this setup, but we're actually going to draw like each ray as a line, because that's what we're doing. We're just essentially creating these lines and then seeing where they intersect certain defined geometry, such as in this case the sphere. And this is exactly what we talked about in episode 2, which is where we covered all of the math. So now we're going to see like how those lines actually exist in a 3D space. So the first thing that I want to kind of pay attention to is obviously this render loop here, because this is the basis for the rays that we cast. This per pixel function is just what we do to each ray to figure out whether or not that ray actually hits the sphere, and then we respond in a certain way, in this case by returning a color, such as pink if it hits, and just black if it doesn't. But this is kind of the real meat of it, because what we do here is we go through every pixel in our image, and for each pixel, once per pixel, we cast a ray. We work out a coordinate between -1 and 1, and then we pass that into this per pixel function to do the rest of the calculation. So this is kind of the ray creation code. So what I want to do back here inside our kind of Hazel setup is basically the same thing. Like I just want to basically grab this, and then I'll come over here and just paste it in. Now obviously this is written in C++, we'll translate this in a minute, but the idea is for each of these kind of pixels, for each of these rays that we cast, I want to physically draw a line inside this kind of 3D space. So how do we set that up? Well, first of all, I mean, final image, get width, get height, let's just set some kind of arbitrary width and height. We'll start pretty kind of sparse here. I might make a width of 50, and you know what, maybe we'll make the height the same thing. We didn't really deal with aspect ratio last time. We probably will cover it today, but for now we can set a width of 50 and a height of 50, which will be 2,500 rays that we'll actually cast here. I'm just going to translate the rest of this into C# and into this kind of setup that we have here. Okay, and now we have this coordinate. We have this coordinate which is supposed to be between 0 and 1. So I'm just going to make it a vector 2 because that's Hazel's vector 2 type. And then replacing the width and height with the width and height variables, we get this. We can still multiply it by 2 and subtract 1 as we did, except this time instead of just setting an image data, I'm actually going to use Hazel's debug renderer to draw a line. So what we're going to do is we're going to draw a line from some kind of origin point. Now, if we go back to this ray tracing setup, you can see that our ray origin was 0, 0, 2, and our ray direction was that coordinate x and y and a -1. So let's copy this code as well. And then back over here, I'll paste it and change this to be a vector 3. And we're left with this. So we still have like a ray origin and a ray direction. Now I can actually put the ray origin into like the starting point of the line. The ray direction will be like the ending point of the line. However, a direction by itself is a bit weird. So we'll kind of grab the origin and scale it along the direction by some kind of length. Now this length I'm just going to declare up here. This is like the visualized length of our line. It doesn't really matter too much, but this is going to affect what we actually see, obviously, when we render this. So this will kind of dictate the length of the line. Ray direction isn't normalized, so this length is not going to be like, 2 meters in this case, but it will be some like arbitrary length. And then finally, we need some kind of color. So I'm just going to pick a nice magenta kind of pink color for that line. All right, now if I build this, come back over here, hit play. Let's actually hide that scene hierarchy panel. And then I'll go back to like the editor camera, but in play mode, you can see we have a whole bunch of rays now. They're a little bit hard to see. I think what I might do is let's just define like some kind of ray color here. And what I want to do is I'll make it black and I'll set the alpha to be like 0.5 or something slightly transparent. And then we can just hit Control-Shift-B and it will kind of live recompile, as you can see, and we have all of our rays here. Let me just make them full black here so it's a bit more clear. I'm also going to just set the line width to be maybe like a bit thicker, like 3 or something. There we go. So now you can kind of see each ray. Now, each of these rays is just generated using, of course, this coordinate. It has like an origin, which obviously is over here, which we've set to be 0, 0, and 2. And then we're shooting them in this kind of negative direction. If we actually showed the grid here, you can see that this is kind of the origin of our 3D world. We've stepped back 2 units, so 2 meters, to get to this point here, because that's our origin. And then we're shooting the rays kind of back in the direction that we stepped back into, if that makes sense. We're shooting them kind of backwards. If this was +2, obviously that's the negative z-axis, and we're shooting the rays that way. Now, in the last episode, we were able to actually like visualize the coordinates by simply setting the pixel to be the color of the coordinate. We can do the exact same thing here. We can just set the ray color to be coordinate. Now we have actually done the ×2 - 1 thing here. So I'm going to go back to just coordinate times 0.5 plus 0.5 for x and for y to get into a 0 to 1 space. And then we can just leave blue at 0, Control-Shift-B, and we'll change that to coordinate y. And you can see we basically get the same result now, which is pretty cool. We can kind of see the bottom left corner of the image that we used to see being black. And then as we go higher, it gets more green. As we go more to the right, it gets more red. And of course, more to the right, I'm kind of referring to from the perspective, obviously, of this, right? So if we look at it this way, this kind of matches what we actually had in the previous episode initially. Now, the density of this is obviously a bit sparse, right? So what I could do is increase this to something like 500 by 500. And we get a solid image. Now, the performance is going to be a little bit bad here because we're drawing like 250,000 lines. But you can see that we get like a solid image, right? So I will be using like some slightly smaller numbers just so that it performs a little bit better, like even that's fine. So overall, I think this is a really good way to visualize what we're actually doing per pixel in the code that we wrote last time. And again, making this a little bit more sparse will make things like a little bit easier to understand. I mean, if I even set this to like 20, which might be too sparse here, what we're doing is from the camera, which at the moment is just like this fixed kind of little point, right, in 3D space. That's what we've done. We've set it to be like the ray origin. From there, we're kind of spitting out all of these rays in different directions, which kind of ends up being like 1 for every pixel that we actually have on our screen. And as these lines kind of get sent out from this point, we test each one of these lines to see whether or not they actually intersect this sphere that we've mathematically defined. So let's go ahead and add that functionality over here. I want to see that sphere that we've actually created inside the code last time. So if we go back to our code from last time, we have this kind of defined radius. Basically from here, I'll just copy all of the code and we'll use that as like our starting point. Let's make this a little bit bigger. So what I'm going to do is paste it into here. I guess we can drag the radius out. This will be like our sphere radius. We're going to replace the dot product into what Hazel's API currently looks like, which is just vector3 dot dot over here, and over here. You can see the code is generally the same, right? So now we actually have the ray direction, ray origin. We have all of this kind of worked out and we have a valid discriminant. Now it's just about what we want to do with the discriminant, right? What do we want to do with the information of whether or not we've hit the sphere? Well, what we're going to do in this case is just change the ray color. So I'm actually going to make the ray color black as it is originally. I'm not going to set the ray color to be based on this coordinate anymore. However, what I will do is just set that ray color to be pink, just like we did for the sphere, if it actually hits the sphere. So otherwise, we'll set it to be black. And if I hit Control-Shift-B, then you can see back here in Hazel, now the kind of lines in the middle here, the rays in the middle are all pink. And if I increase the amount of rays here, let's just move this over. If I increase this back to being like 200 by 200, then you can see we have that sphere image just like we did in the last episode. But now we're kind of drawing it with these lines. And you can see that if we fly into here, actually what I'll do is I don't really like the way this is set up. Let's just bring this ray color down here. We'll set the ray color like initially to this black value, and then we'll just get rid of this branch entirely. I just want to make it like slightly transparent, maybe like 0.2 or something, just so that we can kind of see. Now this obviously depends on the order that it's drawn in, that's why we can't see everything, but you can see that we can still kind of see through it. You can see these rays kind of originate, if I can go slow enough, these rays kind of originate from obviously where all the rays originate, and then we just have these kind of lines which go across, and these pink rays are the ones that end up intersecting the sphere. It has nothing to do with where they intersect the sphere, it's just did they or did they not? That is what the discriminant is telling us, and that is kind of that final image that we get. Now what about aspect ratio? What if we didn't have like a 1:1 viewport, I guess? Well, let's try and like create something that's 16 by 9. So 320 by 180 is a 16 by 9 aspect ratio. If I just rebuild it with that, in the beginning we get the same kind of result, but the distribution of rays is actually different. There's less rays vertically than there are horizontally. The reason why this is the same and we didn't get like some stretch thing is because obviously we're just drawing stuff based on the rays that we shoot, and they're like this. Now in our original code, when we actually stretch the viewport, obviously now we're filling in colors over a greater area, right? That's not what's happening here. We're just mathematically shooting rays. So you can kind of see that if we adjust this aspect ratio here, like if I go dramatic and make this like 18, then you can see that there's just physically less rays obviously vertically than there are horizontally. You can see all of the individual kind of rays here, but vertically we only have 18. And then if we kind of map that onto this area, we get a stretched image. But the math, you can see, isn't really stretched. You're just controlling how many rays you actually send out. So let's set this back to 180. But to actually map this to a larger area, and for it not to be stretched out here, we basically just need to take this x coordinate and multiply it with this aspect ratio. So let's calculate the aspect ratio. That's just going to be width divided by height. I'll just make that a float. And then we'll multiply x with aspect ratio. And now you can see, let me just close this. Now you can see, move our code out of the way. Now you can see that we have like a widescreen view, but this is obviously still like a sphere. It has not been stretched. And so if you apply the same code to the code from last time, you'll get the same result. Okay, cool. So this is looking pretty cool. Hopefully this gives you guys just a deeper understanding of how we actually shoot these rays out. Now there are a lot of problems from shooting out rays from just a single point like this. If you're familiar with a camera frustum, you know that there is such thing as like a near clipping plane, and essentially the frustum you create is almost never like one point. For that reason, we're not going to stick to this kind of thing forever. We'll move to a more traditional camera system which will have like a near clip, a far clip, a field of view, that kind of stuff. And that's going to be really important because as we start to kind of move this around, if we were to, which we're not doing at the moment, the distortion is going to be not that pleasant. So with this current setup, let's go ahead and see if we can actually figure out where these rays intersect the sphere, because now all we're really drawing is whether or not a ray intersects the sphere. If it doesn't, it gets this kind of black color, and if it does, it's pink. But what about drawing like a sphere in 3D space? How does that work? Well, if we go back to our math from episode 2, then we know that once we have the discriminant worked out, we can just continue to complete the quadratic formula to get our actual intersection points. And once we have the intersection points, we can feed them in to that original ray equation to get like an x and y coordinate in this case, or an x, y, and z coordinate in our 3D case. So let's go ahead and do that. So we know that the rest of the quadratic formula is minus b and then plus minus the square root of the discriminant, which we already have, divided by 2a. I'm just going to write that down over here. I probably should get that like LaTeX plugin or whatever for the Visual Studio comments. But anyway, so we have minus b plus minus square root of discriminant divided by 2a. So let's go ahead and implement that. We obviously only need to do this if we know that the discriminant is greater than 0, because otherwise we don't hit anything, and also we probably don't want to square root a negative number. So our t value, we're actually going to have two t values. I'll label one of them as t0 because we have a plus minus here, but t0 is going to be minus b. We'll make this like the smaller one, so we'll do minus the square root of the discriminant divided by 2 times a. And I'll just put this into parentheses as well. That's going to be our t0. That's like the minus variant of this quadratic formula, and t1 is going to be the plus variant. So we'll just change this to be a plus. Those are our two solutions. Now we might only have one solution. That is technically possible, although pretty rare, because that will be like a ray exactly tangent to the actual sphere. But in that case, these will be identical. So once we have these two things, let's go ahead and plug them into the original equation, which is ray origin plus ray direction times length. And this length is going to be t0 or t1. Now these are both 3-component vectors, so therefore this is really just a scalar along them, and the result we get is also going to be a 3-component vector, which is going to be our hit position. Now we do need to calculate this twice if we have two hit positions. I'm just going to go ahead and put these in local scope, so like this. And then for each of these intersections, I also want to draw something. Now I'm not going to draw a line. I'll draw this quad billboard, which is basically just a quad that faces the camera at all times. And we're going to draw it at hit position. Now we need some kind of size, which I do want to control. So let's go ahead and say vector 2 quad size. We'll make it like 0.1 or something. This will be in meters. And then we'll paste in quad size. Now we need some kind of color. So for now, I'm just going to write vector for sphere color, and we'll make it like, I don't know, green maybe. Vector 4, 0, 1, 0, 1. That's green. We'll paste that in. And then I'll copy this and paste it here as well. Okay, let's hit Control-Shift-B. And look at that. We have a sphere. Looks like that size is probably big. Let's make it a bit smaller. Okay, this is cool. So now we can see an actual sphere. I mean, if I hide the line rendering for a second, then this is the result. Like we've just drawn a sphere. And if I make this a little bit bigger over here, let's make it like 0.5 or something. I mean, yeah, you can see we have a sphere, and it's obviously in 3D space now, not in 2D space. There's our grid. You can see also it obviously is to scale and everything. We made the sphere have a radius of 0.5. Each one of these grid cells is a 1 by 1 meter grid cell, so you can see that the radius is in fact 0.5. It is in fact centered at the origin. Everything obviously computes correctly as we would expect. But wait, we can actually take this further. Since we've actually got all of the hit positions over here, let's see if we can apply some basic lighting to this. For that, we need something called a normal. A normal is basically like a directional vector that is going to be, that's actually bigger than I intended, that's going to be perpendicular to a surface. So in other words, in this case, if I just zoom in here and show you guys, a normal for like this area over here would basically be a vector pointing this way. For something here, it might be pointing that way, right? It's like the direction that that face points. So how can we figure that out? Well, in this case, it's actually very, very easy, because we obviously have like the hit position, like we know that it hits here because we're drawing a quad there, and we also know the origin of the sphere. In this case, it's actually just the middle here, which is 0, 0, 0. So what we can actually do is just basically subtract like these 2 points. I mean, subtracting 0 is not going to do anything, but you will need to subtract it just in case this isn't literally centered at the origin of the world. If we subtract these 2 things, so if we take this like hit position and then just do minus the origin of the sphere, we're going to get a vector pointing this way. And if we want, we can normalize it to get like an actual direction. But since we've kind of created this vector, you can see that if we, I mean, it's just a direction, so we can move it anyway. But if we put it here, it is literally the normal, and this will work everywhere. So it's very, very easy to actually calculate the normals of a sphere, as long as you like know where you intersect it. So let's kind of put that into practice. What I'm going to do is actually make like an array out of this first of all, just because I don't want to have to do all of this stuff twice. So these are kind of our 2 solutions. And then I can just write a for loop that goes through this stuff, ti, and hopefully that will give me the same result. So what I want to do is calculate the normal now. So the normal is going to be, as I mentioned, the hit position minus the origin. Now, the sphere origin right now is 0, right? I don't really have to write this, obviously. I'm going to anyway, just so that it makes sense. In fact, I'm going to make it a variable called sphere origin. This is next level programming, making variables for absolutely no reason. But again, it's just so that it actually makes sense. Sphere origin. Okay, so we have that sphere origin at 0, and that's how we calculate the normal. Now, the next step with the normal is we're going to normalize the normal. And then what I want to do to verify this is actually use the normal as like the color for that specific quad, which represents the hit position. So what I'll do is for the color here, I'm just going to write new vector 4 normal times 0.5 plus 0.5. So again, I'm kind of converting it into that 0 to 1 space, because otherwise it'll be between -1 and 1 ultimately. And we don't want negative colors, they'll just be black, that's boring. And then we'll just leave the alpha as 1. All right, and if we Control-Shift-B that, you can see we now get our normals. Now it's a little bit hard to see because I actually don't remember where these rays are coming from. Okay, so they're coming from this point over here, which means that if we look at this, you can see that we get beautiful normals. These colors just represent the normal of each hit position of the sphere. So each intersection, we're drawing the normal as a color. So with these normals in mind, how about we add some lighting to our original sphere color? So what I'm going to do is simply compute the dot product between this normal and a light direction, which I haven't actually defined yet. So let's go ahead and define a direction for our light. Vector 3 light direction is going to be, let's make this like maybe -x, -1, -1 on y as well, because it's going down, and then maybe like 1 on z. I'll then take it and normalize it. Then we'll come back here and we'll do negative light direction, because obviously we're trying to, if I go back to my little drawing view, which is pretty cool, you can see that for this, if our light is like over here and is coming down, we're obviously not trying to compare the coming down vector, which is what light direction is, with the normal vector, because you can see this comparison will give us this kind of angle, right? We don't want that. Instead, what we want is we want to compare it with a vector going towards the light like that, because that will give us a more useful angle. So the dot product of these will actually give us whether or not this is kind of facing the light, and if it is, it'll be like above 0. The result of that dot product it is. Again, if you guys don't know how any of this works, math, brilliant. Click my link in the description below. It's honestly brilliant. Anyway, so this will give us a more useful result. That's why I'm negating it to kind of invert it. So instead of going this way, it's now going that way. And I also don't really want it to go below 0, so we're just going to use a max here to make sure that it doesn't go below 0. So it'll pick the maximum between these two. If this is negative, we'll just get 0. So this is going to be basically like our light, like multiplier, intensity, whatever you want to call it. And so what we'll do is we'll multiply this light with our original sphere color. Now I don't really want to affect the alpha channel though, so let's just do light times sphere color dot xyz. And then we'll obviously make a new vector 4 out of it. By the way, if you're used to C++ and you're seeing this new keyword everywhere and you're freaking out, don't worry. These are just structs, and in C# structs will just be allocated on the stack. So these are most definitely not heap allocations, don't worry. Okay, so we have light times sphere color xyz, and then obviously 1 for the alpha. So let's go ahead and build that. And you can see now that we have some pretty cool lighting. And if I make the size of these quads even bigger, so like maybe 0.3 or whatever, you can see that, like, check this out. We've got a lit sphere made out of like ultimately lines and little quads that we've drawn in Hazel using C#. Honestly, I love this stuff. One more thing I want to show you guys is if we make this a little bit smaller here, I'll bring back the rays that we cast in the first place, because it may not have been immediately evident here, but if we make them a little bit longer, so again, this is just affecting the visualization, right? If we make them a little bit longer, if I zoom into the right place here, you can hopefully see that for each of these pink rays that hits the sphere, you can see how they kind of pierce the quads that we're drawing. It's going right through the middle of this quad. Because that's kind of, at the end of the day, what we're doing. We're seeing which rays actually hit this sphere, and then where, and we're just drawing like a little quad in that exact location. And the rays obviously kind of, they can keep going. I mean, we can define like a maximum and do all of that stuff, but at the moment we're just visualizing lines at an arbitrary length. So this isn't really that like mathematical, but in the case of this sphere and everything, you can see, hopefully, how that's kind of working. And by the way, if we chose to, for example, not evaluate both solutions of the quadratic equation, so let's just say but we kind of just wanted this one over here, and we just, I mean, I guess I can just set this to 1. Then you can see we only get half the sphere, right? We get this side. And then if we set this to be 2 and maybe set this to 1, so we see the other side, that's what the other side looks like, right? So we need to evaluate both of these in order to actually get this kind of complete sphere if we're interested in both sides, which you might be, you might not be, up to you. Now, the final thing that I want to show is, and I could talk about this stuff all day, honestly, and play around with it. I recommend you guys do. I might publish this code somewhere, and obviously if you've got Hazel, you can just open this kind of ray tracing series project that I've kind of created. But otherwise, I'm sure you could easily adapt this C# code to Unity or something like that if you want. But I want to show the effect of normalizing the direction. So ray direction dot normalize. So what happens if I normalize this ray direction? Because I mentioned it might be a good idea to normalize it if you want accurate hit distances, stuff like that. But again, you don't really need to normalize it. But what happens if we do? So if I build that, what you might see over here, and it can be a little bit hard to see. Maybe what I'll do is I might make this a bit sparser, and also, where's the color? I want to make the color solid. I'll just set it to like 1. What's happening here, as you can see, is down the middle, the rays kind of reach this point, but as we get further up, they don't quite go as far. Well, it's because they actually do go exactly as far. The length of them is all 1. Now, it's going to get scaled by this length. So in other words, they're all of length 4 meters in this case. If I put the grid on, you can see that the rays that go right down the middle, they terminate exactly at this grid cell, which is 4. And if I just set the length to 1, so we kind of essentially don't multiply it by length, or if I remove the length from here, then you'll see that they all kind of get to just exactly 1 meter here. And then obviously the ones that are diagonal, they're also now 1 meter in length. That's why they don't get to the very end here, because otherwise they would be greater than 1 meter in length. So that's the effect of normalization. Now, I saw a couple comments last time. I don't really want to talk about this now. I saw a couple comments last time mentioning that if we normalize the ray, we don't really have to do this A calculation, because the dot product of a unit vector with itself is just going to be 1. So in other words, we can just label this as 1 and be done with it. As you can see, we get the same result. Now, whilst true, we don't need to do that. Normalizing a vector is a lot more expensive than just calculating a dot product. Remember, dot product is just the multiplication of each component and then summed up. Whereas to get ray direction, you need to work out the magnitude of a vector, and that requires using a square root. There's division involved in that, so the performance actually ends up being a lot worse. I don't really want to talk about optimization at this stage, but just to kind of show you guys what I'm talking about, if we go back to our original code from the last episode of the ray tracing series, you can see over here that in release mode, my render time's around 3 milliseconds. If I just grab the title bar, you'll see maybe 3.3, 3.1, something like that, right? If I change this to be normalized, but then don't do this calculation, let's take a look at the effect on performance. Look at that. Now it's 4 milliseconds. That's significantly slower. It's like 30% slower. So yes, ultimately, don't normalize unless you really, really have to, because just know that normalization, I mean, it's not the most expensive thing in the world, but it's obviously more expensive than a dot product, and that's why I'm kind of not doing it. And you can see in this case, if I bring back, let's not make this as sparse. And again, the rays are going obviously further. We see the complete sphere. We're just not visualizing them further than this point here. But ultimately, when we look at something like this, you can see that whether or not it's normalized or not, so if I just comment out this normalization, Control-Shift-B, it's it doesn't matter. The sphere still looks exactly the same. All of our normals are correctly calculated. Everything is fine. So in this case, we actually don't need to normalize it. But in general, regarding optimization and stuff like that, I'm not writing this with optimization in mind. Obviously, if it gets to completely ridiculous frame rates and like it's very, very slow, I will have to do some of that. But ultimately, we'll talk about optimization like at the very end. It's much more important that you guys understand the math, and as you can see, it's more than fast enough at the stage that we're currently at. But in general, regarding optimization and like performance, we'll get there. Don't worry. I don't want to kind of start off with putting too much emphasis on that, because as you can see, things are more than fast enough at their current state, and it's much more important that you guys understand the math and make sure that like it's all written out properly, you understand it before you start, you know, taking shortcuts and trying to remove certain things or whatever. Because in a lot of cases, when you're kind of presented with that final optimized version, it's so difficult to see the original math in there that it just looks like magic code and no one knows how it works, and that's bad, and that's obviously what I want to avoid for this series. But yeah, I hope you guys enjoyed this episode. I wasn't exactly planning to make this episode, but I thought that it would just be so cool to visualize some of this stuff. One of the reasons why I actually made Hazel in the first place was because I wanted a nice platform like this to be able to visualize things and teach you guys. So hopefully you enjoyed this. Hopefully there'll be some more episodes kind of like this in the future as well. Next time, we're going to take the code that we've kind of more or less written today here, put it back into our original kind of ray tracing application, and then we'll be able to get into some seriously exciting things. Thank you guys for watching. Don't forget to hit the like button below if you enjoyed this video, and also don't forget to check out Brilliant using my link in the description below. I will see you guys next time. Goodbye.